Hey guys, welcome back to Genius Learning. So today I want to show another classical mechanics problem similar to the previous one, except now we have a glider and a pendulum attached to it of length b. Okay, this pendulum has a mass m and it's driven horizontally by this value here. So it's driven like that, and as it goes, the pendulum is allowed to swing left to right. So let's identify the position of the ball, and seeing as how we have our theta here, we're going to identify this side here as b sine theta, and adjacent over here is going to be b cosine theta, which is below the x-axis, and so our potential is going to be the x-axis. So everything below the x-axis is going to give us a negative potential. Okay, so that's also important to identify before starting the problem. All right, so let's do our position. Okay, so our position of the ball, or bob, as it's referred to sometimes, we got x is equal to b sine theta plus it's being driven by x is equal to a sine omega t. So a sine omega t. Okay, these two terms are used to describe the position of this bob as it's being driven horizontally. Okay, and we have our y, which is underneath the zero, and so we have a negative, or underneath the potential. So this potential here is equal to 0, so anything underneath that is negative, and our y, which is up to here, is going to be negative b cosine theta. Okay, so this is our position. All right, now let's identify the velocities. Okay, we're going to be using the dot notation, so x dot, which just means the derivative of x with respect to time. So everything here is a time derivative. Okay, so the only thing that has time in it is going to be our theta. And so just as a side note, theta t, right, is a function of time. We're representing as just theta, and x dot is the same thing as saying dx dt. So it's the derivative with respect to time. Okay, so our first term here has a theta, which is a function of time, and b stays the same because the length of the pendulum doesn't change. So the derivative of sine is going to be cosine theta, theta dot. Okay, so remember that the theta dot is outside of the cosine. And we have here plus this omega t. We need to take the derivative of this because of the time. And so a cosine of omega t times omega. So that's the chain rule. We take out the derivative of this inside and we put it outside. Okay, so we have a cosine omega t, omega on the outside. Just like we did with the theta dot, it's the same thing. And y dot is just going to be the derivative of cosine theta. Derivative of cosine is negative sine, so negative and negative. We got a positive b sine theta, theta dot. Okay? All right, perfect. Now let's take a look at the kinetic energy of the system. So kinetic energy is represented by T, which is equal to 1/2 mv squared. The velocity could be represented as x dot squared plus y dot squared. Okay, so we're going to use this. So our kinetic energy is going to be 1/2 m All right, we have x dot, which is b cosine theta, theta dot, plus a cosine omega t, omega, all of that squared. All right, so all of this is my x dot term, and now we need our y dot term. So plus b sine theta, theta dot. And everything is in the big parentheses that separates the x dot squared plus the y dot squared. And again, I'm gonna drop the parentheses notation, but just know that this theta is attached to the sign, the theta dot is just outside. All right, so let's FOIL this part out and let's see what we get. Okay, so we're gonna have b squared, theta dot squared, cosine squared theta from the first term. The combination of both of them is gonna be 2b theta dot a omega. So we got b theta dot a omega cosine theta, and then cosine of omega t. Okay, so let's make sure we got everything. We got b theta dot a omega, and then both cosines. All right, and then the last term from here is going to be plus a squared omega squared cosine of omega t squared. Okay, and that's it. Now plus the y dot squared term, which is going to be b squared theta dot squared sine squared theta. Okay, so let's see what we can combine, what we can cancel. So we got here sine squared theta, cosine squared theta, and we have the same constants in front. Okay, and that's something that you should look for. You'll always have that type of situation in most cases when you have to FOIL out these two terms. Things will combine to reduce this large term here. And so if we have cosine and sine together, cosine squared plus sine squared, that's going to be 1. So all we're left with is b squared theta dot squared. And then we're going to rewrite all these terms here because we can't simplify them any further. Okay, so cosine theta, cosine, I'm going to keep these in parentheses because since it's 2 letters, I don't want to confuse the notation. Okay, so we have that. Perfect. So now this is our kinetic energy term, which represents the kinetic energy of the pendulum as it's being driven horizontally to the right. And now let's look for our potential energy. Okay, so the potential energy of the system is going to be U is equal to mgh, which can also be written as U is equal to mgy. Okay, we know that our y is negative b cosine, so we're going to have U is equal to negative mgb cosine theta. Okay, and excuse me. Okay, now let's look at the Lagrangian. So the Lagrangian is going to be made up of the kinetic energy minus the potential energy. And so we have the kinetic energy here. So let's rewrite all of this. And this time here, let's distribute this 1/2 m into all 3 terms, just so it's not confusing when we start taking derivatives. Okay, so I'm going to write this first one here as mb squared theta dot squared over 2. This second term here, since the 2 cancels with the 2 on top, we're just going to have plus mb theta dot a omega cosine theta cosine omega t, and when we distribute this term over here, we have a plus 1/2 m a squared omega squared cosine squared omega t. So all of that is the kinetic energy term, already distributed to 1/2 m, okay? And then we have the potential energy term, which is up here. So minus u, the u is already minus, and so it's gonna be plus mgb cosine theta, okay? So this is our Lagrangian. All right, and now using our Lagrangian, we need to find the Euler Lagrangian or Euler Lagrangian, however you like to say that, equations of motion. So Euler Lagrange equations of motion is d dt, so the derivative with respect to time of the partial derivative of the Lagrangian, partial derivative of what value, what function we need, which is theta dot. Okay, theta is a function of time, so that's what we're interested in. And then we have minus the partial of the Lagrangian with the partial of theta dot, of theta by itself. Okay, so here's theta dot, and here's theta by itself. Okay, now let's do this in parts. So let's see. We're gonna do this term first. So we got the partial of L with respect to theta. Okay, let's look at our Lagrangian. Here we don't have a theta by itself because this is theta dot. Here we have a theta, so let's take the partial derivative of this theta. So the partial derivative of cosine is going to be negative sine, so we're going to have negative mb theta dot a omega sine theta, and everything else stays the same. Okay, and then if we keep looking for theta, this last term here also has a theta. So the derivative of cosine is again negative sine. So we have negative mgb sine theta. All right, and we don't do the theta dot or the chain rule because remember, we're just taking the partial derivative of theta. So we're not doing the derivative with respect to time. So this is what we get here. Okay, so now let's do this term in here. We're gonna do partial of the Lagrangian over the partial of theta dot. Okay, so this first term has theta dot, and so if we take the derivative of it, the 2 comes down, cancels with the 2 on the bottom. We get mb squared theta dot. If we look here, we also have a theta dot, which disappears when we take the derivative, right? Because we're just taking the derivative of theta dot. So we have plus mb a omega cosine theta cosine omega t. Okay, and again, if you're confused about this part, so let's think about if we have the derivative, or let's say the partial of L with respect to x, and let's say the Lagrangian was 3x plus cosine theta, then all we're interested in is the x term, and if we take the derivative of 3x, then it's just going to be 3. See, we drop the x in the same way that we want just the derivative of theta dot, and so we drop the theta dot and we keep everything else. Okay, so just the same way we take the derivative of 3x or a number or constants times the value we're interested in, we drop it and we just have what's in front of it. Okay, so this was just an example, not part of this problem. So now we're done with this term. Let's look for theta dot here and no theta dot in the rest of the problem. So we're left with this, okay? Now the next part, which is taking the derivative with respect to time of the partial of the Lagrangian over the partial of theta dot, is the tricky part. So let's look at that. So the derivative with respect to time of the partial of the Lagrangian over the partial of theta dot. Okay, for this first term here, it's simple. We're just gonna take the derivative of theta dot, and that's gonna be b squared theta double dot. Okay, so again, a side note, if that was confusing to you, we have theta dot is equal to d theta over dt. Okay, and for theta double dot, all we did was take the derivative of theta dot. Okay, so basically it's you can also look at it as the second derivative of theta with respect to time. Okay, so any of these two right here is exactly what's happening here. All right, so the confusing part for this one here is going to be in this term. We have two terms. Let's identify them. We have this term here, which is theta, and it has a function of t, and this term here has omega t. Okay, so we need to use the product rule. I'm going to write it over here. Product rule, which is f prime g plus f g prime, and this here is going to be our f term, this here is going to be our g term. Okay, so let's solve for that over here. I'm going to pull out all the constants in the front. It always makes it easier for me to solve when I'm doing product rule stuff. So I'm gonna write m, b, a, omega, and I'll box up what the product rule comes out to. And so the derivative of f, so the derivative of this first term is gonna be negative sine theta, theta dot, right? Because now we're doing the derivative with respect to t, so time. And so we need to do the chain rule. So that's the first term. G comes along, okay? And now plus this second term here, and the derivative of g. Okay, so the derivative of cosine is going to be negative sine. So let's change this already to negative. And the derivative of this is going to be sine omega t, and chain rule, we have omega that comes out. Okay? So the derivative of this inside with respect to t is just going to be omega. And that's it. Let's distribute this so we have a little more organized here. We have m b squared theta double dot minus m b a omega sine theta, theta dot cosine omega t, and again minus, we have omega and omega, so we got m b a omega squared cosine theta sine of omega t, and that's it. Okay, so this is what we're left with for this term of the Euler-Lagrange equations. Okay, so now let's put them together. Okay, so this is our Euler-Lagrange, and let's see, we have this term first, so we're going to start off with this. So this might be a little long. Let me change the color here because we might get confused. And so let's write all of this, which is our first term. So I'm gonna write mb theta double dot. Okay, we have minus mba omega sine theta, theta dot cosine omega t, minus mba omega squared cosine theta sine omega t. Okay, that's everything here. And then we have minus partial of L with respect to theta, which is this whole term here. So the minus distributes into this term and this term, making them positive. So we're gonna write positive this first term here, which is gonna be mb theta dot a omega sine theta cosine omega t, and positive the second term here, which is mgb sine theta, and all of that equal to 0. Okay, that's a lot. So let's see if we can find things that cancel out. All right, let's see. We got this term here that has mb theta dot a omega, mb theta dot a omega, sine and cosine, positive and a negative. So this term here and this term here cancel out. Nice. So we have something easier to work with. Okay, and again, we can cancel out the m's, right? Because if we divide everything by m, and on the other side, then it just cancels out. All right, and so let's write what we have left. So we have b squared theta double dot. Okay, we have this here, which is minus b a omega squared cosine theta sine of omega t, and we have this last term, which is plus gb sine theta equal to 0. All right, we want to always leave theta dot double dot by itself. So let's divide everything by b squared. Okay, b squared and b squared here. So this goes away. We're left with one of them on the bottom and again here. All right, so finally we get theta double dot minus a omega squared over b cosine theta sine omega t plus g over b sine theta equal to 0. All right, nice. And so we're gonna leave that right there, and that's the equation of motion due to a pendulum with mass m that's being driven horizontally by x equals a sine omega t. Okay?